So, welcome to everybody, and to this new session of Physics 5429, the Advanced Machine Learning course. The plan for this week is to start with convolutional neural networks, which is a topic many of you will probably be very interested in. And then, before we do that, we will recapitulate some of the features of standard neural networks, and we will try to explain why the so-called CNNs, the convolutional neural networks, are that impactful and very, very efficient when it comes to dealing with, in particular, images and classification of images. Now, before we do that, I wanted to remind you of some of the things which we discussed through an email, and that is we found now time for the lab session. So for those of you who are interested, we will have in-person lab sessions every Thursday at 2:45 to 4 o'clock. And the place is the room just below the one which we have normally. And this is physics in the eastern part of the building, 397. So this is a place where people can come and collaborate and discuss the projects, and we will be around and discuss with you and help you with practicalities, etc., etc. One of the other things which we also did was to send you the links to both the lecture for this week, but we also sent you a Jupyter notebook for some of you who is online here could unmute yourself, please. So I see that there are people who have some noise in the background here. Thank you. So we sent you also an example of a physics-informed neural network where we are using PyTorch. We sent you also the files from Rashka's textbook for chapter 14, which is among the recommended reading material. So if we then go back to the Jupyter notebook, you will then find the links as a reading suggestion to Rashka's chapter 14, which also contains how to set up a convolutional neural network using PyTorch. In the lecture notes, which you have here, you will also find examples on how you can use TensorFlow. So for those of you who prefer TensorFlow, this is also a possible options. And then one of the things which we will discuss next week, and we will start scratching this today, is how we can actually develop our own convolutional neural network. So there are links also as well to other lectures, and feel free to take a look at these links. So what I want to do first now is to bring us a little bit back to what we discussed in connection with neural networks. And that will serve also to motivate the link from a standard neural network where all the input nodes are connected to the first nodes in the hidden layer, and all the nodes in the subsequent hidden layers, they are fully connected. That means that we have a dense matrix which connects the different layers with the weight parameters to be determined. And that leads to a set of what we normally call affine transformations, which in our case translates into matrix-matrix and matrix-vector multiplications. Now, this set of operations becomes or leads quickly to very, very large matrices. And that at the end slows down the efficiency of the codes. So when it comes to CNNs, they represent in a certain way through the mathematical process of convolution. They represent an effective way of reducing the dimensionality of the problem, and at the same time to keep track of the essential features. Now, there's one thing with CNNs which you should keep in mind. So CNNs are really tailored to specific types of problems. So if you're dealing with a set of images, then a CNN would be trained to that specific set of images, which then leads again to often a classification problem. However, before we move on, I just wanted to slow down the pace a little bit again and just remind ourselves about the basics of a neural network, because some of these ingredients are essential also when we are developing our own code for convolutional neural network. So let's jump into the whiteboard before we go back to the basic structure of a neural network and how we would set up a code. And then we're going to dive into the convolutional neural networks. So let's just bring ourselves a little bit back in time to last week and the previous week and remind ourselves a little bit about the structure of a neural network. So because the basics of a neural network is something which we will also encounter when we are setting up a neural network and when we are setting up a recurrent neural network. So let's just remind ourselves of some of the basic properties here. Basics of NNs, neural networks. So one thing is that we define a model or architecture. So I often use these as synonyms. And this architecture contains an input layer. This input layer connects with a series of hidden layers. This is where we have the different unknown parameters which we need to train. And these hidden layers have a given number of nodes or neurons or units as they are normally called, with a specific number of nodes, hidden, so-called hidden nodes. And these hidden nodes and hidden layers, they have a set of parameters which we used a variable theta as a common container for. So this theta would then contain the weights of the different layers. So the first hidden layer, there would be a set of bias parameters for the first hidden layer. We had a second hidden layer. We can have as many hidden layers as we want. And then we ended up with a final hidden layer, which is the output layer. And that has also its own parameters. And we put an uppercase letter L for that. So these are the parameters which we train by the backpropagation algorithm. So we have a hidden layer, an input layer, and then there is obviously an output layer. And that output layer produces an output from our training. And that output is then compared with the target values. So we will then compare the output of the network, which is our model. So you can just think of it as you fitting a polynomial. And when you fitted a polynomial, you want to compare that fit which you made with the target values which you have. So the compare them with the target values. And these target values are normally compared with the output through a so-called cost function or loss function. This function C is a function of the unknown parameters theta, and it is a function of the input variables, which we labeled with an X, and it's a function of the output variables, which we labeled with a Y tilde. This is what the network produces, and it's a function of the target values. So the output layer produces an output. Y tilde, and then the target values are given by the Ys. Then the training takes place by implementing a gradient descent algorithm. So this is the first part here is actually the model or the architecture of the network. And this defines the complexity of the problem. Then what we have next is the training part. Training of the parameters. So the parameters theta, and this is done through the feed forward stage. Where we just send through from the input layer to the output layer, produce a final output. This feed forward stage is accompanied with a back propagation stage, plus the back propagation. And in this specific case, the back propagation is nothing but a way to find the gradients. So the back propagation part gives us the gradients, which we then use to determine the parameters. So that means that what we need at the end is the derivative of this cost function with respect to the unknown parameters. And through this training, where each feed-forward stage and back propagation stage defines one iteration, we update these parameters theta. We typically then have, for a given hidden layer, L, we would then have a set of parameters which get updated continuously in terms of their respective gradients. So there would be a dc of d theta of L. And now I'm just putting this generic variable theta, which now encompasses both the weights and the biases of a hidden neural, of the different hidden layers and the output layers. Now these gradients are then by introducing a so-called learning rate. So that leads us to a set of methods to optimize the learning rate. You can use a fixed one, and then we are normally stuck with what is called a plain gradient descent method. Or we can have different ways of updating the learning rate, which then are normally called schedulers or updating algorithms, and some of the more famous algorithms, so that for every such iteration, we would then update the learning rate. And there are famous methods like this ADAM, which stands for an adaptive momentum method, that's widely used in order to update this. It contains some information about the gradients. And we have a root mean square propagation. We have adaptive gradient, ADAGRAD, and many, many other methods. And as we have been discussing many, many times, this is a field which is an active field of research in machine learning, namely how to find the best possible way to update this parameter, the learning rate. Now, what you see here, if you had the second derivative of the cost function, this would be nothing but Newton-Raphson's method for finding the roots of a function. This is the essential starting point, that we make an assumption that we can tailor expand around an optimal value. So when we iterate these quantities here, then we are searching for the optimal parameters theta so that they do not change according to a prescription that we have chosen after a given number of iterations. So these gradient methods, or the training part, is essential when we are now setting up the neural network. Now, when we then go back a little bit to the architecture, there is something which we should also mention here, which we did not put here, because the architecture contains also two elements, one which we discussed here, that's the specific cost function. And you would typically have cost functions for classification problems, which then could be based on a binary classification problem. And then you end up with what's normally called the binary cross-entropy function. Or you can have a regression problem where you're fitting a function, and then it's very natural to use something which is like the mean square error. And then you would optimize that one, and then find the optimal parameters. Now, and then there is a further quantity which enters the architecture, and which is called the activation function. So when we look at the structure of a neural network, we will typically have an input X. This is the input layer, when we are just writing this in a generic graphical way. And we discussed examples last week of simpler neural networks. And then we feed this in to the first hidden layer. And here there is an activation function, which we label as a sigma 1. And that is a function of the weights for the first hidden layer. And it contains all the biases for the first hidden layer. And then this can continue, and then it produces, so the circles are outputs or inputs. The boxes represent mathematical operations which are performed in each layer. So this will then produce an output, which you're now just writing as a vector or eventually as a matrix. And this goes all the way, then continues to the next hidden layer. We would have a sigma 2 here. And then we have new parameters, W2, there's a B2, and this continues all the way till the final layer, where we have a sigma L. This has its own weights again, which needs to be hit in this iterative process, and then a B of L, and this produces the final output, which we label with this the Y tilde, but we are going to put a label here as an A of L here. And that is then eventually fed into the cost function, this function C, and then we have the target value 1, the values which we want to reproduce. So in essence, what we have been dealing with is a set of affine transformations, where typically this first function, just to give you one example, contains an input, and where this C1 is now given by the weight parameter multiplied with the inputs. And right now, I'm not specifying whether these are vectors or matrices or just scalars. So last week, we looked at the simpler cases where we had scalars and vectors and eventually a matrices, plus this parameter B, which you have here, V1 here. And then what you end up with is a set of such affine transformations. We are dealing with the dense matrices, which are being multiplied with dense matrices, eventually dense vectors. So the important thing with a neural network is also the so-called activation function. And in the program which we have online here, all these elements are then included. So we have an activation function, which is a very important part of the architecture of the network or the model itself. So when we have set up a set of hidden layers, it's pretty common in the training to use the same number of hidden nodes. You would typically start running with one hidden layer. You increase this to 2 hidden layers. And if that improves your results and you get a perfect fit, then you're happy. If not, you would continue to play around with the architecture of the network. And every time you make it deeper and deeper, you get more and more parameters. And normally this is the reason why we have this naming deep learning, in the sense that we can make the network as deep as we want. But clearly, the deeper, the more parameters we need to train. Now, the activation function is then one of these elements of the architecture. And this is something which we should mark here, because that is a debated issue, which is the best activation function. And if you go online and search for activation function using machine learning, you will see tons of stuff. So this becomes another type of parameter which enters your model definition. Then clearly we also have the cost function, which depends on the type of data which we have and the type of problem which we have. So these are important parts of the architecture. So architecture is this. If we go back to the previous slide, we have the training of the network, and that involves methods like gradient descent or the various families of gradient descents. And this is a field, as I said, of active research. Then finally, we have the last term, which is a set of hyperparameters. So we can actually, if we want, we can then add additional tuning parameters. And this is something that leads to the big disappointment for many, that there are so many parameters we end up training. And where is the magic of a neural network? So typically what we have is a cost function, which could be a root mean square. So we're just going to rewrite this as an input dependent function plus the parameters we're training. And then we can add parameters, which then could be given as a norm 2 of the weights, for instance. This is a pretty common choice. So that's the norm 2 squared. Normally called an L2 hyperparameter regularization. We could have a similar quantity, the cost function, the original one which we have, which could be the mean squared error. But we could have the norm 1, which is another probability. So these are hyperparameters which would then be included in the setup of the cost function and the training of the problem we want to optimize. So these weights are obviously parameters which are parts of the training. So in essence, what we're doing now is we are optimizing a different function. It gives us more flexibility, and for many, many cases, you can actually obtain a better fit to the data by having additional parameters. Now, said that, we also have hyperparameters in the training part. So we also have the cost for in the activation functions. There are hyperparameters. So that's another set of hyperparameters which we need to fix. So these are parameters which we normally don't train. That means that these are fixed parameters when we start the calculations. So we can have if we're using a RELO or an ELO type of activation function, there will be parameters which define these functions, and they're normally set at the beginning of the calculation. And then you can rerun the calculations and tune them. So we have hyperparameters there. We would have in the gradient descent, we have something which is called the number of epochs, the number of times we actually perform the gradient descent optimization. Plus, if we're doing a stochastic gradient descent, there's something which is called a back optimization, which means that we split the data in small chunks, and then we play around with these as parameters. Now, when we come to convolutional neural network, we are going to meet more parameters. Now, one of the things which probably, I don't know if it disappointed you, if it surprised you, when you look back at the training part with the backpropagation algorithm, this is nothing but the chain rule. So if you think of a neural network and you want to be perhaps a little bit arrogant, you could say that a neural network is nothing but basically mathematics. It is essentially you setting up the chain rule and calculating derivatives and then performing various types of multiplications. And then you do this back and forth. It sounds like a little bit arrogant, but the basic mathematics, even if we spent a lot of time on it, is actually pretty straightforward. Now, the fundamental aspect of a neural network lies in the universal approximation theorem and the flexibility which we have when we are setting up a network with many different parameters and different depths. So that gives us a lot of flexibility in the fitting of a function. And the universal approximation theorem simply states that what you have then is an approximation or a model given by the architecture in terms of specific activation functions, which allow you to find an approximation to any continuous function within a certain level. So it's a pretty strong statement. Now, said this was meant as a kind of reminder of what we're doing here, because this links also well with our discussions on convolutional neural networks. So let's go back to the Jupyter notebook, which we have for the code itself. And this is something I would like you to take a look at if you're interested. So let's just go back to the Jupyter notebook here. So last week, we went through some of the basic mathematics of a neural network, but we didn't discuss the final implementation. Now, we have a set of Jupyter notebooks, which you should also have gotten, where we simply discuss how to build our own neural network code. Now, at the end of these slides, you will also find how you can set this up with TensorFlow and how you can set this up with PyTorch. And these are examples which we welcome you to take a look, and it's up to you how you actually want to implement things. So many of you would most likely be interested in what's normally called a physics-informed neural network, which means again that you would often end up using either TensorFlow or PyTorch, which give you efficient programming environments for implementing these things. So again, there's just a list of some of the books which you can look up as additional literature. And if you're interested in the setup in PyTorch, then you can actually go to Sebastian Braschka's website for his book and download all the Jupyter notebooks. And the same with David Foster's and Bali and Gavra's textbooks. You have access through their GitHub addresses to all the codes. And essentially what you find when you download the Jupyter notebooks is that you have chapter by chapter of their textbooks. So I really recommend you, depending on which programming environment you want to use, to either use TensorFlow, if that's something you find more efficient for you, or PyTorch, which is well described in Rashka's textbook. And alternatively, you can actually write your own code. So this code which you see here is the result of something which was done by two former students which followed this course, actually. And this was a summer job. And I mentioned to you that last time that we have the possibility of 1 to 2 summer jobs in perfecting these codes or adding material, etc., etc. This is something which we can discuss, and I know that some of you have already sent an email being interested in doing that. So the code here, which you will see, contains all the elements which we discussed now. Now, you may ask, why am I just repeating all these things? And because some of you have seen this before. The reason why I repeat it is because the basic elements which you see here, they enter also the setup of a convolutional neural network. So what you have done for a standard neural network is something which will simply be reused in a code for a convolutional neural network. And the first class you will encounter is the one which sets up the training with the learning rates and updates of the learning rates. So as I said, the simplest possible learning rates for these gradient descent methods is just the use of constant. So this class scheduler actually schedules a way to update the learning rate. And in this specific case, we have a constant learning rate, which is just set here. So that means you just keep the same value. And what is normally done is that this learning rate is treated as a parameter, and you will train your network with an array of such parameters. So you could start with a learning rate which is 10 to the minus 5, which means that your gradients will barely move, to a learning rate which would be 10 to the minus 1, or even 1. That means that you will be making large jumps, and you may eventually not reach the optimal values. So tuning the learning rate is one of the big issues. And you could say, now, why shouldn't I calculate the second derivative, which enters Newton's method? Now, the reason for that, as many of you know, is that the second derivative is a matrix. And if you have, let's say, 100,000 parameters, this is a matrix of dimensionality 100,000 times 100,000 because it contains a second derivative. That's essentially the Jacobian. And you have to invert the Jacobian. And you don't want to do that, period. And then we have standard methods. So these are topics which have been discussed in earlier courses, and we will not discuss them here. But it contains the momentum upgrade. There is adaptive gradient, which you can use if you want to. So feel free to use these methods. There is an ADA-grad with momentum, which can be done. There is a root mean square propagation, which is another popular way of updating the learning rate with information about the gradients, as you can see from the algorithms here. And if you go into the textbook by Benjo and Goodfellow and Colville, in their chapter 8, they have a detailed discussion of these algorithms, if you want to revisit these algorithms. So as I said, this is material which we have covered in Physics SDK 4155. And we will not spend time on that here. So ADAM is the most popular method, and this is the method which since 2014 has more than 150,000 citations. So this will be the first part. There's a description of the usage of the different learning rate schedulers, how you would use them, how you can set the different parameters. So eta is used hopefully in a consistent way as a learning rate. You can use the Adam scheduler, etc., etc. Then, when you're done with that, you have to define the cost function. So this is another property which needs to be set up. And depending on the type of problem you're having, you can have a binary classification problem. You can have a mean square error. So when you see this OLS here, this is the ordinary least squares or just the mean squared error. And this just returns the difference between your output value and the target value. There is the logistic regression function, which is used for a typical binary classification problem. And then there is the cross entropy here, which is normally often used in a classification problem with more than just two classes. So the binary classification problem is often the one which is the simplest one to use. Then we have the usage of automatic differentiation, which you can implement either using JAX or other methods. And this is something which you should also consider including, because that sets up the derivatives of the functions you want to deal with. There is a whole class of activation functions. So we have the identity here. So if you're dealing with a regression type of problem, your output layer normally just spits out the input from the previous layers, and that simply returns what we call the identity. Alternatively, if you're dealing with a binary type of problems, the sigmoid function is much used. If you have an output layer where you're dealing a classification of more than just a binary class problem, then there is the softmax function which is being used, etc., etc. So these are a whole series of types of activation function, and the ReLO function is one of those which are widely used. You have the TAN-H function and many, many other ones. So what you will see here is just a limited number of activation functions. And you will find also their derivatives. For some of them, it's actually easier to calculate the derivatives, pre-calculated, and set up the derivatives analytically. And what you will find then are just simple implementations of this. I'm not going to run through everything. And then when you now have the neural network, what you have then is a new class here, which performs the feed-forward part, and it contains also the backpropagation part. So this is essentially the training of a neural network. So I invite you to take a look at it. We are not going to run the calculations here. This is something which often is much better to look at when we meet at the lab sessions. But here you have an example on how you could set up a neural network according to what we went through in the previous weeks. So I'm just going to scroll down here because I also wanted to point out, so there are just the different examples. This is the feed forward and the backpropagation part. There are types of functions you can test with. There are linear regression types of problems. There are classification types of problems. So you can just then play around a little bit with these different functions. So in this course here, which in a certain sense assumes that you have some knowledge of basic machine learning. So please have me excused for those of you who have not taken a course in machine learning first. But the many of the basic elements which you encounter here are things which are common to essentially all the machine learning methods. So I just wanted to point down here to the application of TensorFlow when you're setting up your own neural network. And it's then typically it's common to use Keras as an API on top of TensorFlow, which was released by Google in 2015. Then what you typically would do then, as an example here, you would collect your data. This is a data set. This is a data set of 100 numbers from 0 to 9. So you have 10 categories or 10 classes. And that means that your activation function for the output layer would typically then be given by a softmax function, which is one of the more popular ways of implementing the output. So I just wanted to bring up the way you would import TensorFlow. So you would set this up as a sequential neural network. You need to import different layers. You have an input layer. You have a dense layers for the hidden layers. You need to include the type of optimizers. The regularizers deal with the hyperparameters you can add. And then if you're dealing with a classification of categories like this 100 numbers, you would typically include this categorical option in TensorFlow. Then you would split the data into train and test, which is pretty common in machine learning, with an 80% often allocated to training. And then you would then define the number of epochs, the batch sizes. These become hyperparameters. Your structure is then defined by, in this specific case, 2 hidden layers. And these hidden layers have 100 neurons in one and 50 in the other one. It's pretty common to have the same number of neurons in the hidden layers. The categories here define the number of outputs. So in this case, we have 10 handwritten numbers from 0 to 9, which we want to classify properly. And here I'm now setting up the different hyperparameters, lambda, which I have here, and the learning rates, which span from 10 to the minus 5 to 10 to the power of 1. And same with these parameters. So these become parameters, and then you can use the type of optimizer. So you can now see that I'm adding, so Keras as an API with TensorFlow allows you to simply set up things in a very easy way. So you have a sequential model, obviously. So it starts with the input layer, moves to the first hidden layer, second hidden layer in a sequential manner. That's why we use sequential here. And you see now that the first hidden layer has a set of neurons, which is given by 100. It has the sigmoid function as an activation function. It has a norm2 regularization parameter, an L2 here, which takes the parameter lambda, as we discussed previously. It has an activation function here for the second layer, which is the same as the previous one. It's actually common in the training to use the same activation function for all the hidden layers. And then, since this is an activation and a classification problem, then we have 10 classes or 10 categories. We will typically use the softmax as an output activation function. And the optimizer is a standard stochastic gradient descent, and it takes the learning rate as an input. So this does not use any fancy methods to improve on the learning rate. So that means that we are basically using a constant learning rate here. But you can define which kind of scheduler you want to. So you can now see that defines the type of cost function or loss function. So it's common to use either loss or cost. And this is the cross entropy for categories. We are using an optimizer, stochastic gradient descents, and the metric is the accuracy. So this is the metrics for the model which we have chosen. And in our case, this means that what we are doing now is simply to count the number of correctly classified events and divide that by the total number of events which we have. So if you have 90% correctly classified, your accuracy would be 0.9. If you have 100 events, so you have 90 which are correctly classified, divide by 100, and that gives you simply 0.9. And the way we would do the training then is simply to run through the different hyperparameters. We perform the training and then use the trained data to make a prediction, which is now done with the data which were not included in the training, and that's the test set which we have included here. And that uses the accuracy. This is the way we evaluate the model which we have produced. So remember now that the architecture or the model which we have is now given by the setup of the neural network. And this can then be, so I'm not going to run this because it's not that important here. There's also an example on using PyTorch for classification problem. So in PyTorch, this is something which we haven't discussed yet fully, but we will bring this up during the lab sessions in more detail. If you go into the textbook by Rashka, you will find in chapter 12 and 13 of that textbook, you will find a very good discussion on how to use PyTorch in a setup of a neural network. But again, here you can see that you define the number of hidden layers. You define this to be 2 layers. You define the type of output. You define the type of activation function for the output, which is a sigmoid. In this case, you have a ReLU function in the hidden layers, and you are setting up the number of hidden nodes, etc. You have the feed-forward part, which is set up here. You define the classifier. You define the type of loss function, the binary loss entropy with BC loss. You define the type of optimizer here, the learning rate, the number of epochs, the number of batches, and then you run over the number of epochs, and then you run over the batch size, you make your prediction, and you train the network here. So there is a backward step and a feed-forward step. So you can then, at the end, you can compute the accuracy, and this is essentially the way you would set up this with PyTorch, which is actually allows you an almost equally simple way of doing things as you've been having with TensorFlow. So this is something which we will leave more to you, which one of these frameworks you want to use, or if you want to follow the examples which we have in writing your own code. This is also equally, how to say, interesting for us. I mean, this is very much up to you. So the it's often a matter of faith which approach you want, or which package you want to use, whether you want to use TensorFlow or PyTorch. I find PyTorch pretty simple to implement. One of the things which has always driven me crazy is every time I make an update, I have to reset, re-update TensorFlow, and sometimes it doesn't work properly. And I waste hours on detective work on finding which packages was not updated correctly. And with PyTorch, it's very seldom I've been having that kind of problems. So this is very much up to you. Now, the thing which we are going to do now, after this repetition and survey of the different possibilities which we have, we are now going to go back to the setup of convolutional neural networks and why convolutional networks are that interesting. So what you can say is that one of the main motivations which you will see after the break is that if we have typically images with many pixels, high resolution images, then the number of weight parameters which we end up training becomes enormously large. So just to give you an example, if you have an image, just one image with 100 times 100 pixels, this would define 100 times 100, which is equal to 10,000 input nodes. And then if you have 100 hidden nodes, that means that your dense weight matrix, which you would have in a standard neural network, would then define a matrix, a weight matrix of dimensionality 10,000 times 100. And this will be the parameters you would have to define just for the first hidden layer. Then you would have more hidden layers, which means that the dimensionality and the time you would need for training would become very large. So the CNNs, as I will call them, instead of saying convolutional neural networks, have been extremely successful in image classification tasks. And it's a particular type of a feed-forward neural network. And it gained a lot of attention, and it led actually to tremendous improvements in machine learning for computer vision. Now, prior to neural networks and convolutional neural networks, one of the standard methods for dealing with images was to reduce the dimensionality using the singular value decomposition algorithm. And some of you may be familiar with that. So you would typically take a matrix, which in our case could represent the different pixels, and you would perform a singular value decomposition. With that singular value decomposition, you had all the orthogonal eigenvectors of the orthogonal transformations, and then you could use these vectors to make a projection. That means when you make a projection of a full basis, you project it down to a smaller set of vectors, then you could reduce the dimensionality of an image and then store that one, but you would have to keep track of the orthogonal transformations which you performed. So that becomes quite, to say, computationally intensive if you have images with a large resolution. So around 2010 or slightly before that, then the CNNs really took over, and they have now become the standard method for computer vision. And one of the inventors, Jan LeCun, actually received the Turing Prize for the development of convolutional neural networks and the theory behind it. So one of the basics of neural or CNNs is actually that you are able to extract the essential features. And that's a key component to the performance of any machine learning algorithm. And traditionally, if we look at the standard machine learning models, they would rely on input features that may come from a domain expert or based on computational feature extraction techniques. And certain types of neural networks, such as the CNNs, they can actually learn these features from raw data that are more useful for a particular task. So it's pretty common to actually consider these convolutional neural networks and the different layers of such a network as a way to extract features of images. And we will come back to that after the break.
Welcome back. The main aim in the next series of lectures, is actually to discuss the setup of a CNN and why we do CNNs. So certain types of these multi-layer neural networks with many hidden layers, and then in particular this deep convolutional neural networks, which have been extremely successful in image recognitions, they construct what we normally call a feature hierarchy by combining low-level features in a kind of layer-wise fashion in order to form high-level features. So if you're dealing with images, which is one of the main areas of applications of CNNs, then what you would say then is that low-level features, if you're looking at, for instance, a house, like the edges of the house, the doors and the windows, they can be extracted from earlier layers. So there is a filter which is being applied to an image. And this filter is normally applied to a small region. And then through a series of such filter operations, the image or the process here leads to forming high-level features. And these high-level features can form more complex shapes, such as the general contour of a building, a house, or even animals. Now, one of the things which classifies or distinguishes a CNN from a standard neural network is what we call a sparse connectivity. So if you think back to what we discussed before the break, a standard feed-forward neural network has all nodes being fully connected with the nodes in the next layer and the nodes in the previous layer. This means that you often end up with affine transformations with large matrices, and we will see examples of this when we scroll down some of the slides here. Then there is another feature which is called parameter sharing. So the same weights and biases are then used by different patches of an input image. So as a direct consequence of that, of these two ideas, a sparse connectivity and sharing of parameters, then replacing a conventional, fully connected feed-forward neural network, as we've been discussing earlier, with a convolutional layer that substantially decreases the number of weights in the network. And you will see that as an improvement, and it's often seen that as an improvement in the ability to capture specific features. Now, that leads to a very important thing to keep in mind when you're dealing with pre-trained convolutional neural networks. Now, these networks are normally tailored to specific tasks. So the CNNs are not limited to image recognition only, but they have also lately been applied to regression type of problems. But the filters are often really tailored to specific tasks. So you need to keep that in mind when you're using some pre-trained convolutional neural networks, like those which we produce by popular data sets like ImageNet where you have millions of parameters which have been trained in order to reproduce tons of different types of images. So the structure of a neural network, which we are going to go through now, contains several such steps, but this filtering plays a very important role. And that has been a standard approach in imaging. So I mentioned before the break the application of the singular value decomposition algorithm. You have also been using Fourier series in imaging. And these are all ways to either shrink the size of an image in order to store it, and then have information which can bring you back to the restoration of the full image. So if we now look at the difference, you can say that the difference is that the CNN architectures makes an explicit input, in essence that the inputs are images, and which allows us to encode certain properties into the architecture. So when I said this, that CNNs are often fine-tuned to specific tasks, this is actually a very important aspect which you should keep in mind. Then these then make a forward function more efficient to implement, and it reduces the amount of parameters in the network. So as we've been discussing neural networks in the standard way, what's often also called a multi-layer perceptron neural networks, they are defined as affine transformations. So you receive a vector that's multiplied with a matrix, which contains the weights, and that produces an output. And you have a series of such matrix vector, matrix multiplications. So when you consider images, or even sound clips, which are also a very popular area of application, or similar data, they often have an intrinsic structure. So when you think of applying a standard neural network, you may often not have an idea of internal structures or specific correlations in the data which you could use. And then you could apply blindly a feed-forward neural network to try to train a specific model. Now, when you're dealing with CNNs, on the other hand, you know that the data may have some specific structures. You know, the house has corners, it has windows, it has doors, it has roofs, etc., etc. And that means that you can have one or more axes for which you can order your data, like the width and the height axis for an image, the time axis for a sound clip, etc. And one axis, which is normally called a channel axis, is used to access different views of the data. It could be red, green, and blue channels of a color image, or the left and right channels of a stereo audio track. So these features, as you can see here, so I'm just staying at this kind of overarching level, they are normally not exploited when you set up a standard feed-forward neural network. And in a feed-forward neural network, the way we've been discussing them, you could just think of that as a brute force implementation of a training algorithm. And then all the axes, all the features are treated in the same way. And you don't take into account specific topological information. Like when you're thinking of a house or a building, you know that that has some specific features which distinguish a building from, let's say, an animal or a human. And this is actually where these specific filters which you apply to an image, they come into play. So if you now just look at some of these dimensionality problems which we have, so suppose you have an image of a size 32 by 32, so you have 32 pixels. This is not a very high resolution image. A typical high resolution image has hundreds of pixels, and it has the standard so-called free color channels. This would be define the number of input nodes. So that means that you would have 32 times 32 times 3 input nodes in a standard feed-forward neural network. And these will be fed into, let's say, if you have only one fully connected neuron, so one node in the hidden layer, then you would actually have 3072 weights to train with just such a petite number of hidden nodes in the hidden layer. And this clearly scales up when you have more. If you have 100 nodes, you have suddenly 3072 multiplied with 100. And if you have an image which is 200 times 200 times 3, then you have, with just one hidden node, you have 120,000 weights to train. So you can quickly see that this leads to a blow up in the number of parameters which you need to train. So this is just a repeat of what you would have with a regular neural network. So I'm just going to scroll down a little bit here because I'm going to use the whiteboard as well. But typically a standard feed for a convolutional neural network would have an input image, which is then being scaled down. And this can be replicated in many, many smaller images, or it has specific patches from an image, specific areas, which are then scaled down. And then you would train parameters on that. And then you can repeat that process. And then at the end, you would flatten out the data and feed that one into a standard feed-forward neural network. So if you wish to stay a little bit along this kind of dimensionality discussion, you could think in a field like signal processing, and this applies to imaging as well. You could, it's pretty common to design filters. And when you apply a typical neural network, suppose you have an input vector length 10 to the 6th, then you can construct a neural network with only one hidden layer with, let's say, 10,000 nodes. That means you will have 10 to the 10th weights to be determined, together with 10 to the 4th biases. And that clearly means that you end up with a size of parameters which is actually way too large to deal with in an efficient way. And keep in mind then that now we are not exploiting any features in the data set. So one of the things which we often want to, when we look at a specific problem, is to try to extract some specific features of the problem before we grind everything through a specific algorithm, like a feed-forward neural network or a CNN in this case here. So when we are looking at take a bird's eye view on the feed of a convolutional neural network, you have specific stages. We obviously have the input, and this could be an image, or it could be a sound sequence, or it could be something else we want to train a convolutional neural network with, where we know that we can extract specific features. If we do that, we have, after the input layer, there is normally a convolutional layer. And in this convolutional layer, we can produce replicas of the image, but where we have filtered down the size of the image. And then, so we could use 10 filters, 12 filters, how many we want. After that, there is a activation function which is applied to the output of this filtering. This is often done with the activation function of the ReLU type. And after that, there is a pooling layer, which we will come back to and discuss what that is actually doing. That is actually another way of downsampling the size of the problem. And then finally, we have a fully connected neural network where we would train with the input which comes from these different stages. We would then just run that through a standard neural network. So in the convolutional layers, we have parameters to train. So we would train them by the standard backpropagation. So backpropagation pops up again. The ReLU layer has a fixed hyperparameter for the activation function. So that does not have trainable parameters. These will be parameters which we set before we run a convolutional neural network. Then there is a pooling layer, which is a further downsampling of the output which we have. And in that specific case, what we have is another set of hyperparameters which tells us how we are going to do this so-called pooling. And there are two types of pooling. One is called the max pooling, where we will take patches of an image, and then we would pick the largest value. And then we would collect all these largest values and downsize the image. That is one way of doing it. Another one is average pooling, which we will come back to. And when you've gone through these three stages, you have reduced the dimensionality of the image, to specific features which we think are the essential ones. Then, when you have that, it's pretty common just to feed that through a standard neural network. And that is again trained by the standard backpropagation algorithm. So this is the kind of overarching structure of a feed-forward neural network. And we can draw this graphically in the following way. If we now just switch over to the whiteboard, just to slow down the pace a little bit again. So let's do that. So the basics of a feed-forward of a convolutional neural network contains essentially this 4 basic stages. So a typical CNN, and you will find images in the slides again, but I'm just using the whiteboard to slow down the pace a little bit. So a typical CNN contains 4 stages. In principle, it's actually 2 main stages, but I'm splitting one of them into 3 elements. So you would have one, the first stage is actually where you would apply convolution. So the convolution is a way to filter down the size of the image. So you would take specific parts of an image and then use them through the convolutional process and build up many smaller images. So you have first is several. It can contain several convolutionals in parallel. And this is the mathematical process of convolution. In the slides, you will find links if you are not too familiar with the mathematical process of convolution. A typical area of using convolution has been Fourier transforms. Some of you may have taken a course in mathematical methods, and you may have encountered the mathematical process of convolution, and that's often done in connection with Fourier transforms and Fourier series. So several convolutions in parallel, and we are going to look at several examples in the coming. So we have convolutions in parallel to produce what we normally will call a set of lower resolution images or lower dimensionality images. So this is also seen as a dimensionality reduction. And the hope is then that these convolutions then tailor specific features. When you're done with that, and in this case here, we have parameters, weights and biases, which are trained by backpropagation. Trained by backpropagation. So the backpropagation algorithm, which is nothing but an application of the chain rule, is applied to the convolutional layer. So that means that that has a specific training path. Then the output from this convolution stage is then run through a nonlinear activation function. So we run this through. And this is also a way to reduce the dimensionality again. Run through a nonlinear activation function, which is normally of the ReLU type. So I'm just writing this as a ReLU type. And that contains only hyperparameters. This is often also called a detector stage. So you have the convolution stage, and then you have this so-called detector stage. And here we have only hyperparameters. If we are using more complicated types of activation functions, so we have only hyperparameters here. And these will be parameters which are defined prior to us running the neural network. So that means if you want to tune them, you would have actually to rerun the calculations with a new set of hyperparameters. Then the next stage is actually a so-called pooling stage, which is a further dimensionality reduction part, which we are going to discuss in more detail. So there is a pooling stage, and that contains also hyperparameters. So there is no backpropagation, no training of weights. So to further reduce the dimensionality. And here also, we have only hyperparameters. This could be the number of the size of the patches of an image, which we want to scale down further by using, if we're using something which is called max pooling, we could have a slice of this image, which we have trimmed down, which could contain 3 times 3 pixels. And then we would take the largest value, which comes from the application of this ReLO function. So that means that if you then have a 3 times 3 small part of the image, which you have trimmed down, you will then keep only the one which comes with the largest value from the nonlinear activation function. And in that way, you're trimming it down from a 3 by 3 small image to just one element. So that's a way to further reduce the dimensionality of an image. So that's the pooling stage. And in this case, we have only hyperparameters as well. So there is no training with the backpropagation part. So let's just emphasize that, because it's a little bit important to see where we have the training. So if we go back to the previous case here, we have this case. And if we now look at the first part here, then we have parameters which are trained by backpropagation. So this is where we have a training element. Then the final stage here is something which I have brought together into flattening. So you just flatten out your data in terms of a one long vector, plus that this is fed into a standard feed-forward neural network. So you flatten out the results. This is just a manipulation of the results which you produced, plus a feed-forward neural network. And here you have training of weights and biases using backpropagation again. So let's emphasize that again. So we have the training where we have backpropagation. And then for the other two parts, we actually have just a set of parameters which we're setting up. So the way you can illustrate such a network would be something like this. So you can have some input layer. This is then sent into what normally has as a common denominator the convolutional stage. Let's just write this as a conv stage. But that contains 3 elements, as we have seen. So there is the mathematical process of convolution. So that is a convolution itself. This has then a further dimensionality reduction of the input parameters with pooling and the so-called, the ReLO stage. Was a little bit too rush here. So we have a ReLO stage here where we now filter through the values. And then we have a stage here where we reduce the dimensionality, which is now the pooling stage. And a network can actually contain many such stages. That is actually pretty common. So you can redo this again and again till you have trimmed down the image to a dimensionality, which then is applicable for a standard feed-forward neural network. So in this stage here, we would flatten out the results, flatten plus a feed-forward part. So this is in essence what we might say as a bird's eye view on a convolutional neural network. So tailoring these filters is something which is a kind of art. And many of these imaging filters have been particularly designed to specific tasks. So let's now go back to the Jupyter Notebook and take a closer look at the mathematical process of convolution. So what we're going to take a look at now is actually how do we implement this specific stage. And when we're done with that, we're going to move over to the ReLO stage, and we're going to look at the pooling stage. So the convolution itself contains also some additional hyperparameters, which are normally fixed before we run the calculations, because there are specific ways of performing the convolution, which leads to a hyperparameter called stride. There's going to be a hyperparameter which is called padding, and you will see quickly why we have these additional hyperparameters. So in a certain sense, many people feel a little bit disappointed because you're handed tailoring everything to some specific tasks, and then you have a series of hyperparameters which you need to play around with. So the convolutional stage has in itself a new set of parameters, so let's list them. So let's now focus more on the stage of convolution. And that introduces parameters which are fixed before we do the training. So keep in mind now that the convolution has parameters, weights and biases, which are trained by the backpropagation algorithm, but it also introduces a set of hyperparameters which define the filters. So these hyperparameters are typically given by number k, which is the number of filters which we apply. That's one. Then we need to define a new parameter f, which is the spatial extension of a filter. And you will see that quickly now in some few examples on in the Jupyter Notebook. Then there's another parameter which is called the stride parameter. And this tells us how we operate on the original image, which may be set up as a matrix, and how we perform the filtering. So stride parameter. So these are normally set before we actually run calculations. And then we have a further parameter, which is called P, which is called the padding parameter. And the reason for why we include this padding parameter is that this is a way to hinder that some of the features which are transformed would appear in only some of the cells in the transformed image. So a typical set or common settings which are used widely in CNNs are the following. So you would have a filter which can be a 3x3 filter. So these are square represented by square matrices. So a 3x3 filter. You can have a stride, which we haven't shown exactly what it means till now, with s equal to 1. You can add zeros around the image or the matrix elements, because an image is translated into a matrix typically. And this is often done in order to make sure that some of the information is replicated in several new cells in the transformed image. Another type of a filter which is widely used is a 5x5 filter. I'm neglecting the color channels. If you have the standard 3 color channels, it means that your filter will be a 5x5 times 3. And then you have an S equal to 1, and you can have a padding, which is equal to 1 or 2, which are pretty common ones. There is also a common option is to have a stride equal to 2, and then the padding is often optional. So I'm just leaving that open here. So these are common filters which are often used, and we are going to see examples of how we are going to set up these filters. So let's go back to the Jupyter Notebook and take a closer look at some examples of convolution and what that means mathematically, and how we would typically represent that in a convolutional neural network. So let's just scroll down here, and this is just a quick reminder. So you can have an image with just one color channel. So this can be just a non-color image, black and white one. So you have 28 times 28. You can have a convolutional filter where you produce 32 new images. So when you have a 5x5 filter, that scales this down to 28. Actually, it does 28 by 28, 32. You can do some pooling, which we will discuss a little bit later what that means. And then you scale it down to 14 times 14. And then you can do a new convolution where you have a filter of 5 times 5, and you produce 64 new images. You can perform a new pooling where you reduce the dimensionality, and you end up with 7 times 7 times 64 images. And then this is then flattened and then fed into a feed-forward neural network. And that tells you the number of input nodes which you would have, which in this case would be 10,024. And then you would have 10 hidden nodes. That means that the total number of weights here would be 10,000, roughly 10,000. Instead, if you just run through this image, you would have 28 times 28, and then you would have to have the additional nodes here. So in a certain sense, it's not a big dimensionality reduction, but what you've done now is to reduce the original image in terms of many, many smaller images. Now, so the key idea in the mathematics is based on the process of convolution, and the mathematical expression for this is expressed in this integral here, and you can have a discrete version of it. So you could now think of you measuring the position of a given car, just to give you examples. So X could be the position. And these positions as a function of time here could be riddled with noise. And then you have some filter W, which then filters away the noise so that the final image or the final result has in a way filtered out the noise which you wanted to get rid of. So this mathematically, what you see here, this is nothing but the mathematical expression for the process of convolution. And you would often see that written in this specific form. You have S, X, asterisk with W, and as a function of time here. And that is the mathematical process of convolution. So let's look at some examples. So the way you would look at this discretized is simply in terms of this infinite sum here. Now, normally your sum will contain a discrete set of values where these x's and w's are non-zero. So that means that you would reduce the number of floating point operations which you need to do. But in essence, what we're going to apply now on two-dimensional objects, this is a one-dimensional object, is this mathematical operation here. Why is this interesting? So let's take a look at an example here, which many of you may have encountered, because this example here gives you the basic mathematical operations which are at play in a convolutional neural network. So you may think that this example here has nothing to do with convolution, but actually you can rewrite a polynomial multiplication in terms of the mathematical process of convolution in its discretized shape. So think of you having these two polynomials, which you want to multiply. Now, a very stupid way of performing this multiplication, if you write a code, is just to write P times S. This is not very efficient from a computational point of view, as it leads to many more floating point operations. And we know that when we perform this multiplication, we will have a polynomial of degree 5, because the length of this alpha 0, alpha 1, alpha 2 of that vector, which contains the parameters, contains 3 parameters. So that's a vector of length 3. This is a vector of length 4. And we have a third order polynomial times a second order polynomial. So that means that we will end up with something like this, when we perform the polynomial multiplication. Now, as I said, to just write P of t times S of t is not a very efficient way to implement it. So how would we implement this in a more efficient way? Now, one thing, for this specific example, we can actually go through the calculations, and you will see that delta 0, which is the 0th order part of the polynomial, is simply alpha 0 times beta 0. Delta 1 contains alpha 1 times beta 0, alpha 0 times beta 1. And then subsequently, we can just run through all the constants which we have here. So this would be a more efficient way of actually performing the multiplications here, the polynomial multiplication, by setting up these coefficients. Now here you can do it by hand. It's a very simple case, but you can automatize this in terms of either the process of convolution or efficient matrix or matrix vector or vector multiplications. So let's see how we can do that. So this type of example here contains in a way the essence of the mathematics of convolution. So next week we are going to also look at how we do this explicitly in a convolutional network. Now, one of the things you see is that for the alphas, except for these two values, all the values are 0. And for the betas, we only have 4 values, which are non-zero. We could write this out as a discrete convolution like this by just blindly summing from minus infinity to plus infinity. But we know that there are only 3 alpha parameters and 4 beta parameters. So you could rewrite it as a double sum like this, or you can rewrite it in a better way. So this will also have some few operations which are redundant when you look at this formula here. But if I have a delta y, I'm summing from a value of k. So if I is equal to 0 here, I should have 0, 0. So in that specific case, I'm actually summing from m minus 1, which is the length of the array alpha. And this is actually then, here, I would have this alpha of k. I would rewrite that in a slightly more compact way, which you will see below here. So this is still not as efficient as we would like to have it, because you can replace this k here with information about I, so that you don't include terms which are 0. So just keep that in mind. This is just a further rewrite, but it's still not as compact as we would like to have it. You can continue along this line, and you can rewrite this in terms of a matrix, which now contains these alphas along one of the sub-diagonals, and similarly alpha 1s and alpha 2s, and multiply with a vector beta. So you're actually rewriting everything now in terms of a matrix times a vector. Now, the process of convolution is a commutative process, which means that you can rewrite it in terms of another matrix which contains a beta and multiply it with the alpha zeros. And I leave this to you guys to figure out which one of these is the most efficient way of doing that, whether this operation here or that operation is more efficient. So you can compactify this, or you can change it a little bit in terms of a new terminology, where you can think of the largest one as being your input and the filter being defined by the smaller matrix or vector. So what you could think of now, if we want to apply this to the language of CNNs, you could think of this as your inputs, which is then filtered by a smaller object, and then hopefully gives a more efficient way of representing the same type of information. So these matrices which you see here, they have a name in the literature, and they're actually called Toeplitz matrices. And the standard way, if you leave out the recent progress when it comes to Fourier transformations, because you can actually rewrite a Fourier transformation in terms of these Toeplitz matrices. That's a very interesting topic. The Toeplitz matrices is then a matrix which runs like this, and it has this specific property which you see listed here. And the standard way of doing the convolution is to rewrite everything in terms of the input variables in terms of a Toeplitz matrix multiplied with a filter. It doesn't need to be a square matrix, and there's actually these matrices are also closely connected with Fourier series, because this multiplication operator by a trigonometric polynomial, which is compressed to a finite dimensional space, it can actually be represented by such a matrix. So if you're interested, feel free to take a look at how Fourier series are used in the CNN calculations. That's a very active area of research nowadays. So feel free to take a look at that. Here we will just stay with a more traditional approach. So the above problem can actually be more generalized. So you could now think of this vector alpha, which we had. We just rename that with a W to indicate that that's a weight, because that has a length equal to 3, whereas the parameters beta we had, we replace that with an X, and this X now has a larger length than the filter, and then we could simply rewrite this in terms of the convolution operation. If we go to two-dimensional objects, which are those which we're more interested in, you could now think of you having an input object of dimensionality m times n, and this is the filter, which is often also called a kernel, k. You will often see this W being called a kernel. You will also see this X being called for an input image, I. So these are just different notations which can be used. And that typically leads an output here. So when we are going to apply this convolution, this is normally done by these operations which you see here. So it's a commutative process, which means also we can rewrite this equation in terms of these interchanged operations here. And it's common to actually use in the literature something which is called cross-correlation instead of convolution, although it's always referred to as convolution as well. So mathematically, these are the type of operations which we end up in the convolutional stage. And if you look at this in more detail, what you could think of is that you have an input matrix X, which has a dimensionality 3 times 3. So you could think of this as your original image, and then you have a 2 by 2 filter W. So you would have a matrix like this, which now represents your input. And then you have a filter, which looks like this. So we are going to discuss a little bit next time this parameter, which is called stride. But I'm going to give you a small homework for next time when we meet again, and we are going to set up the basics of a convolutional neural network code. Take a look at this article here, because that is something we will discuss in more detail next time, and what it means with this quantity stride. So stride s equal to 1 here means that if you think of these two elements, these two first ones, and the two next ones, so that means x0, 0, x0, 1, x1, 0, and x1, 1, they are multiplied with a filter. And then we just move one step. So that means that we take these two guys and the two below here. So my pointer doesn't highlight everything correctly here. So stride 1 means that first we take this 2 by 2 subblock, and then we just move one step, and then we take the next 2 by 2 subblock and multiply with a filter. And then we go down here, one step down, and then we have this subblock, which is multiplied with a filter. And finally, we have this subblock, which is multiplied with a filter. That is essentially the operation which is performed when we perform the convolution. And if we take this expression here, we can actually rewrite it. So what we get when we perform these operations, we get now a 2 by 2 matrix, which is the output. We started with a 3 by 3 matrix, and by the filtering, we are now down to a 2 by 2 matrix. But you can rewrite these operations by defining a new vector. So you can actually flatten out the inputs as a vector X of length 9 and a matrix W prime with dimensionality 4 times 9. So your input could now be flattened out like this, and you would have a new matrix which looks like this. So what you would do then, when you have this new matrix, then this is an example again of these tuplets matrices. Then if you have a matrix like this, because you have along this subdiagonal, you have along this one, you see that you get the same matrix elements, you can actually rewrite the convolutional process as a matrix vector multiplication, where you now have this W prime times this X prime, and that means that the convolution which you're performing can then efficiently be implemented as a matrix times a vector. Very much similar to the case which we had previously. So these are some of the basic mathematical operations, and you can see that exemplified in this simple image here. So where you could have a filter which looks like this. And next week, we are going to discuss this feature of padding, which means that you can add zeros here. And one of the reasons for that is if when you perform such an operation, you actually risk that the information about the corners is just transferred into one only of the matrix elements which we transform. And then it's pretty common to just increase the size of the input matrix by just adding zeros. And as we will see next time, that means that some of the results here on the corners, they will appear in just more than one box. This is something which we will discuss in more detail next time. So the mathematics of a convolutional neural network is something which we can rewrite efficiently as matrix vector multiplications, where we have introduced these tuplets matrices. That's one of the ways of doing it, and that's the way we have implemented in the code, which you will see below in the notes here. So next week, we are going to continue further the discussions. We will discuss more about pooling. We will discuss more about the detector stage, where we look at the usage of the activation functions and what that is doing. And we will discuss these hyperparameters called pooling and stride, and see how we gradually can reduce the dimensionality of an image in a series of subsets, and how that at the end leads to a smaller dimensionality, which is then fed into a standard feed-forward neural network. But keep in mind, as an overarching message, that what we are doing now, we are designing filters which are particular to the specific type of problem which we are dealing with. So a CNN, when it's trained, is something which is trained to a very, very specific task. So if you have trained on images of cats, you may not use that convolutional neural network which has been pre-trained to classify houses or buildings.